Welcome to another lecture in the iMath Tutor Screencast lecture series. I'm Dr. Regis J. Sorinko, founder of iMath Tutor. The topic of today's lecture is a rocket on a string. How much string do you need? The problem is actually posed on Math, a Facebook group. And what we'll do here is we're just going to give you the problem as it was posed on that page. Consider that we shoot a rocket by an angle theta of elevation, and its flying trace is a parabola. Also, we connect a piece of string with the rocket to measure its flying distance and after the rocket hitting the ground. Normally, when theta is not too large, the length L of the string pulled out would be equal to the horizontal flying distance d. However, if theta is too large, L would be greater than d, so what is the greatest value of theta to keep L equal to d? There's a lot packed in there, and so what we'll do is we'll formulate the problem mathematically and take a look at the problem systematically. What we're going to assume for our viewers is that you've had freshman physics and you know how to solve Newton's equation for a particle moving in a constant gravitational field. So, suppose that a rocket is fired from the origin of a coordinate system with an initial speed v0 and an angle theta between 0 and pi over 2 from the positive x-axis. Follows from Newton's law that the x and y position of the rocket at a time t after launch are given by x of t equals v0 t cosine theta and y of t equals v0 t sine theta minus g over 2 t squared. Here g is the acceleration due to gravity. Now, the rocket hits the ground after launch. Notice we'll get this by setting y of t equal to 0. The right-hand side is a quadratic and it has two roots. Clearly t equals 0 is one of the roots. This is the second root. So that's when the rocket is back on the ground after launch. And we find by substituting t sub f into our expression for x of t, the horizontal distance, maximum horizontal distance traveled by the rocket. That is the horizontal distance it travels when the rocket hits the ground. We know it's a maximum because this is an increasing function of t. Now what we want to do is we want to eliminate t from this expression for y and look at it as a function of x. To do that, we look at this expression and we solve for t in terms of x, substitute into the expression for y, and we arrive at this somewhat messy looking thing. And we want to simplify it. But before we do that, let's summarize what we have here. And we're going to simplify this by de-dimensionalizing the equation. That is, we're going to introduce two new position variables, eta, which is y divided by x sub n, and z, which is x divided by x sub n. We'll come up to this expression, divide by x sub n. That'll give me eta here, z here, but it'll turn one of these factors of x into z, but I'm going to have an additional factor of x, so I'm going to have to multiply and divide by x sub n. When we do that and work through the algebra, that rather messy looking expression at the top of the page reduces to this rather nice looking expression at the bottom of the page. Eta equals tan theta, z times the quantity 1 minus z. Now we know that z runs between 0 and 1. Eta runs between 0 and tan theta over 4. This quadratic reaches a maximum at z equals a half, and that maximum is a 4, so that's where that comes from. So here we have summarized what we've arrived at so far. Now, for theta fixed, the distance of the rocket from the origin as a function of z is given by this expression. This is just using the Euclidean distance. Now we can restate our problem. We want to know that for what values of theta does the equation rz of theta equals 1 have exactly one solution in the interval 0 to 1. So we're just going to recast this a little bit. I'm going to take r, square it, move the 1 over, so that becomes r squared minus 1 equals 0. Substitute for r squared, square both sides of this, substitute in, and this is what we arrive at after factoring out, after a bit of factoring. And if you'd like, you can pause the video at this point to work through the algebra. So we clearly have one root when z equals 1. That's not very interesting. That's when the rocket hits the ground, it's a distance 1 from the origin in these scaled coordinates. So we want to look at the second factor, and we'll call that second factor p of z, or z, tan squared theta z cubed minus z squared plus z plus 1. And the question now becomes, when does this polynomial have exactly one root in 0, 1? So what we want to do is we want to find the locations of the roots of these this polynomial. Now it's cubic, so we know that it'll have always have at least one real root, regardless of the value of theta. What we now want to show you is that that real root is negative and therefore unphysical, so we don't have to worry about it. Now, we have that when p of 0 equals 1, and that's just plug in 0 here for z, that's clear. And as z goes to minus infinity, the polynomial goes to minus infinity. Notice z cubed dominates, this is positive, this goes to minus infinity, so the whole thing goes to minus infinity. We can conclude from this that there exists a z tilde such that the p of z tilde is negative. And that z tilde, so there exists a p of z tilde less than 0, such that p of z tilde is also less than 0. Now polynomials are continuous everywhere, consequently the intermediate value theorem applied to the interval, closed interval z tilde to 0 implies the existence of a z star in the corresponding open interval, such that the polynomial vanishes at z star. So we know what we've shown now is that we have at least one negative real root. We want to now show you that that is a unique negative real root of p. So we're going to take z1 less than z2 less than 0, and we want to show that p of z1 is less than p of z2, so that on the interval minus open closed interval minus infinity to 0, we have a strictly increasing function. Therefore, it can only cross the axis at one point, so that the root is unique. Now, this is a little bit of algebra. So again, if you'd like to work through it, feel free to pause at this point and work through the algebra. Now, what we want to note here is this inequality. How do we arrive at that? Well, notice here, z1 and z2 are negative. I got a minus sign, so that's positive. Obviously, 1 is positive. We've got a square here, square there, so both of those terms are positive. Both of these factors are negative, so the product is positive. Tan squared theta is positive. So this whole thing is positive. However, z1 is less than z2, so the first factor is negative. So that gives us this inequality, and therefore this root is the negative real root is unique. Now what we want to do is show that the other real roots, if they exist, have to be on the intervals 0 to 1. So let's suppose that zeta is greater than or equal to 1. In that case, zeta cubed is greater than zeta squared, so this is positive. And this is going to be positive because you're greater than or equal to 1. That's positive. So all of the tan squared is positive. All the terms on the right are positive. So P of zeta is greater than 0 if zeta is greater than or equal to 1. So there are not going to be any roots on the closed open interval from 1 to infinity. It follows that if P has any additional roots, it must be in the open interval 0 to 1. Okay, so let's look at the existence of the real roots of this polynomial in addition to the negative one that we've already found. The discriminant of a cubic polynomial q of z, which equals a z cubed plus b z squared plus cz plus d, is delta, and it equals 18 abcd minus 4 b cubed d plus b squared c squared minus 4ac cubed minus 27 a squared d squared. And this discriminant can be used to characterize the roots of the cubic as follows. When the discriminant is less than 0, q of z has a single real root and 2 imaginary real roots. When the discriminant equals 0, q of z has 3 real roots, at least 2 of which coincide. And when the discriminant is greater than 0, q of z has 3 distinct real roots. So let's find the discriminant for our polynomial p. You can pause the screencast at this point and work through it. So we're just doing substitution, though. Here's our a as tan squared theta, our b is minus tan squared theta, our c is 1, and our d is 1. So making those substitutions into this expression, we get that. We then work through some simplification, do some cancellations, and pull out some common factors, and this gives us our discriminant. And what we want to look at here is this thing actually factors. So you can use the quadratic formula to factor this. And what we want to note here is obviously tan squared theta is not going to be equal to 0 as long as theta doesn't equal 0. So on the interval 0 to pi over 2, that's not going to be equal to 0. This is negative. 5 times the square root of 5 is greater than 11. So this is negative, and tan squared is positive, so this will never vanish. So this is the factor that we have to be concerned with in determining the sign of our discriminant. And so what we end up with is our discriminant is less than 0 if tan squared theta is less than 11 plus the square root of 5 times 5 over 2. It equals 0 when tan squared theta equals 11 plus 5 square root of 5 over 2. And it's greater than 0 when tan squared theta is greater than 11 plus 5 square root of 5 over 2. So putting this all together, what we find is that a rocket fired from the origin of a coordinate system at an angle theta from the horizontal will have a maximum distance from the origin equal to its maximum horizontal distance from the origin, and achieve this maximum only upon landing if theta is less than the arctan of the square root of 11 plus 5 square root of 5 over 2. When theta equals this arctan, the rocket will have a maximum distance from the origin equal to its maximum horizontal distance traveled, but it will achieve this maximum once during flight and once upon landing. So this is that maximum distance that we were seeking. And finally, if theta is greater than the arctan of 11 plus the square root of 11 of the quantity 11 plus 5 square root of 5 over 2, then the rocket will achieve a maximum distance from the origin during flight. This maximum will exceed the maximum horizontal distance from the origin. Now a word from our sponsor. Our services and products from iMathTutor are face-to-face tutoring for any university student that can meet with us in State College, PA. This is also true of, we will also work with professionals, and online tutoring for graduate students and professionals worldwide. Actually, currently, we're now loosening up this restriction, graduate students to any university student worldwide. We also sell quick reference guides and practice exams with detailed solution sets for Penn State Math 141, Calculus with Analytic Geometry 2, and these are distributed by Nittany Notes. You can visit Nittany Notes online at www.nittanynotes.com. Study materials for other courses will be added as demand dictates. If you'd like to learn more or arrange a free consultation, visit us at https://imathtutor.org, or you can email or call us. Our email is at help@imathtutor.org, and our phone number is 814-317-6284. Thanks for watching, and stay tuned for more screencasts coming soon.